This is the second video on pulse width modulation, and what I've done is I've directed you to go and look at this video on YouTube, which is an excellent example of or description of how pulse width modulation can be done. Now it is possible, as you've seen in this specific video, that you can really make use of different devices to like a trip 5 timer to get the desired duty cycle. We can also change the frequencies, but the main purpose is, of course, to change the duty cycle, and the duty cycle refers to the high level and the low level on a specific waveform. So if I can just quickly go to this specific sketch here, as we've seen in that specific video, uh, the duty cycle is determined by the on time and also the off time. And if we look at this specific, the line I've drawn here, if the duty cycle is 100%, then it will always be a 1, and if the duty cycle is a 0, it will be a 0. In this specific case, let's assume this one is around about 25% or 30%. That means 30% of the time it's on, and let's say then 70% of the time it is off. So what I'm going to do with this example of mine is I'm going to explain to you how to do pulse width modulation by making use of a 100 hertz uh, pulse to do the pulse width modulation with. Now, I want to do this example making use of the 8051, and if you go to higher frequencies like something like 10K, then this microcontroller is actually becoming too slow. So if you really want to make use of high frequencies, you must use a faster microcontroller like the AVR. But in this example, I'm going to show you how to do pulse width modulation at a frequency of 100 hertz. So that's going to be my fixed frequency. So that means there's a certain period, and that means also there's a certain, that period can be calculated. And if we calculate this specific period, you will see that it comes out to be 10,000 microseconds. That is what this specific period is for 100 hertz. So I'm just taking an example here of, let's say, 25% duty cycle. If I take a 25% duty cycle, that means that for 2,500 microseconds of the time, the total time it will be on, and 7,500 microseconds it will be off in that specific frequency. So also what I'm doing in this example is I'm making use of an ADC which is connected. In our case, we have done this in a specific subject, and we've got a development board which we've connected the 8051 to in a specific configuration. And I'm going to make use of this ADC output to give us the duty cycle. And with the way I'm going to work with this thing is I am going to say that if the ADC output is 255, then that means that the duty cycle should be 100%. So what we can do, in other words, then, is to incorporate some sort of a scaling factor. And this is exactly what I've done here. And I've said if we read the ADC and we multiply that by a scaling factor, we should get to the duty cycle. Like for instance, if I use maximum values, then if the ADC is an output of 255 and the duty cycle must be 100, the scaling factor is 0.3922 in actual fact. There's another 2 there. So any output that I get from the ADC will be multiplied by 0.3922 to give me the desired um, duty cycle. So I'm just taking an example here, and I'm saying if the ADC output is 64, then that translates to 64 multiplied by 0.3922, which is 25% duty cycle then, in other words. So your high time must be 25% of the total time, and your low time must be 75% of the total time, which means that your high time is going to be 25, because that's what I will be setting as the duty cycle, multiplied by 100 microseconds to give us that total 2500 microseconds in a 100 hertz frequency. So I'm going to take this further now with an example and just do the calculations with an example, and then what I'm going to do is to generate from this example, I am going to generate some sort of a formula that can work for us. So I'll say what the question here is: what is the count if the duty cycle is 25%? In our case, we are making use of an 11.0592 megahertz crystal. So if we make use of this crystal here, that means that the machine cycle time, we've calculated this before, is 12 times the period of each and every pulse, and that works out to be 1,085 microseconds. That's the one machine cycle time. So for a delay of 2,500 microseconds, I can then calculate what is the count that should be used in this specific example. So the delay is 2,500 microseconds. We know, so this is known to us now, this value here. The machine cycle time is known to us, and then it means how many counts do I need in my timer. If I'm talking about the 8051, I need a certain number of counts in that specific timer. And we can then calculate this, and you'll see that this works out to be 2,500 microseconds divided by 1,0851 microseconds, and that then comes to a count of 2,304. So if I've got a count in my timer of 2,304, that means I will have a delay then of 2,500 microseconds. So my start point, then that can really then quickly translate to the start point. Where do I start? The start point will be 65,535 minus 2,304. It's actually supposed to be 36 here, but it's so close, so I'm just going to keep it as 35. So the start point then is going to be 63231, which is translated in hex F6FF. And that means basically then that 6F will be placed in timer high 0, and FF will be placed in timer low 0. And that also then means that your timer should be used in the 16-bit mode if I want to accomplish this. So this is the high time for this specific duty cycle, or this duration, which is 25%. Now let's quickly look at how to generate a formula then for the high time. How do I generate the formula for the high time? So I'm just going to work backwards now, and I'm going to say, okay, your start point is 65,535 minus that 2,304, which we've already calculated. And this 2,304, that was calculated by dividing 25,000 microseconds by 1,0851 microseconds. And the microseconds, of course, cancels out. And we also said, but this specific 25,000 was actually derived from the duty cycle, which was anything between 0 and 100. And in that specific case, we said, remember, ADC was 64, so this is why DC, the duty cycle, would have been 25 multiplied by 100, still with the divide by that same value. And if we look a little bit further now, we will see that the duty cycle, we received the duty cycle by multiplying the ADC with 0,3922. That's the 100 and that's the 100, still divided by the same value. And then we are actually sitting with a formula, how to generate the formula for generating the high time of your duty cycle. And this formula can then be applied in this specific device, and it will actually work for any duty cycle from 0 up to 100. That will translate to the high time. So I'm going to stop this video here, the second video, and then I'm going to show you in the next video, I'm going to show you how to calculate the low time, how to generate the formula for the load time. So for now, um, just move over to the video number 3, and we will continue with that one. Good, thank you.